Welcome to The Explainer. Today, we're unpacking a really high stakes fundamental battle that is currently tearing through the artificial intelligence industry. It's a massive debate over the very architecture of machine intelligence itself, and there are literally billions of dollars riding on who ends up being right. On one side, we have the dominant language models you already know and probably use every single day, and on the other, a radically different approach to building AI, one that learns much more like a biological animal.
If you look at the analytics of AI growth right now, the sheer scale is just mind-blowing. I mean, in early 2026, big companies like OpenAI closed a history-making $110 billion funding round. The primary goal of this astronomical investment? To just keep pouring unprecedented compute power into scaling up large language models, or LLMs. The prevailing belief among these industry giants is pretty straightforward. If we just keep scaling up this specific architecture, feeding it more text and more compute, we are eventually going to reach artificial general intelligence.
But then, right in the middle of all this, you see this staggering contrast. Jan LeCun, who is one of the 3 Turing Award winners, known globally as the godfathers of AI, and the former chief AI scientist at Meta, just walked away from that exact scaling strategy. Instead, in early 2026, he launched a new startup called AMI Labs, closing a $1.03 billion seed round. This massive investment is built entirely on the premise that the $110 billion LLM approach is fundamentally flawed. Okay, let's dive into this. Why exactly would one of the core architects of modern deep learning literally walk away from Meta and publicly call the current path to superintelligence a multi-billion-dollar dead end? Well, to unravel this mystery, we really have to look under the hood, at how these systems actually process information and learn about the world. At a foundational level, current LLM architecture relies on something called autoregressive generation. Basically, whether you're chatting with GPT or Claude, the system is calculating the statistical probabilities for a sequence and then predicting the single most likely next token, whether that's a fragment of a word or a pixel in an image. Now, it's incredibly powerful at extending a sequence, for sure, but LeCun argues this is essentially reactive System 1 thinking. It's kind of like relying on pure instinct and muscle memory rather than deep reasoning, because it generates output sequentially, token by token. Early errors compound super fast. It manipulates the statistics of language flawlessly, but it completely lacks a true underlying understanding of physical causality. LeCun actually proves this limitation mathematically by comparing training data volumes. The biggest LLMs process essentially all the digitized text humanity has ever produced. That's roughly 10 to the 13th bytes of data. But compare that to a 4-year-old child. A human child, just by keeping their eyes open and passively observing the world, absorbs 10 to the 15th bytes of data. Actually, to put that into perspective, that is 50 times more data than the biggest LLM, absorbed entirely through vision, not text. Language, it turns out, is just a super thin, highly compressed slice of reality. You simply cannot learn how the physical world works from a medium that low bandwidth. Now, what's really interesting about this slide is the core architectural contrast it highlights. On one side, generative word models try to guess exact pixels or tokens, reacting step by step. But on the other side is LeCun's alternative, JEPA, or Joint Embedding Predictive Architecture. Instead of predicting exact surface details, it predicts the general vibe or abstract concept of a scene in what developers call a latent space. It totally discards unpredictable noise and focuses purely on semantic meaning. And that is what enables what we call System 2 planning, actual long-term forward thinking. Think about how you mentally plan your commute before even leaving the house. That is exactly what a true world model does. Look at the hierarchy here. You have a configurator modulating the system, but the real cognitive engine is the world model interacting with the actor. Unlike an LLM that just reacts to a prompt, a true world model acts as an internal simulation engine. It allows the AI to imagine the consequences of its actions, evaluate them for potential costs or errors, and plan complex, multi-step action sequences under uncertainty before it ever makes a physical move. LeCun summarizes this whole philosophy perfectly. He says, the real world is way more complicated than a world of language. Picture watching a video of a ball rolling across a table. A generative model wastes enormous amounts of compute power trying to predict every exact pixel, the shadows, the dust particles, maybe a trembling leaf outside the window. But most of that is completely unpredictable noise. JEPA simply discards that noise and focuses strictly on the underlying physical concepts, the ball, its velocity, the hard surface of the table.
Because we aren't rendering every single pixel, the analytics of AI growth shift drastically in favor of efficiency. Meta's image JEPA model, for example, trained a massive vision transformer in under 72 hours on just 16 GPUs. Meanwhile, traditional generative rivals took 2 to 10 times more GPU hours to achieve even worse error rates. Because JEPA models don't waste capacity on unpredictable details, they are vastly faster and so much less resource-intensive to train. Let's move to and see how this builds from just theoretical math into some seriously futuristic technology, tech that will soon include robots in our daily lives. Meta developed JEPA 2, a video-based model that passively watched over 1 million hours of unannotated internet video. Through passive observation alone, just like a biological animal, it learned intuitive physics. Then, researchers gave it a mere 62 hours of raw robot data. The result? Zero-shot deployment on Franca robotic arms in completely unseen labs. It learned how the physical world works just by watching, and then successfully applied it to physical robots. No way, right?
The climax of this robotics experiment is absolutely stunning. In pick-and-place tasks, JEPA 2 achieved up to an 80% success rate without any task-specific training or reward functions whatsoever. But look at the compute speed. A generative baseline model called Cosmos took 4 full minutes to compute a single robot action. JEPA 2 took just 16 seconds per action. It is drastically faster because it isn't wasting computing power trying to generate visual noise.
Of course, big companies like OpenAI and Anthropic push back hard against this narrative. They correctly point out that their LLMs are already writing software, passing bar exams, and generating hundreds of billions of dollars in revenue. They firmly argue that their scaling laws will eventually lead to superintelligence. Well, LeCun's contrarian rebuttal to this is incredibly sharp. He says, the fact that something works doesn't mean it's the right path. Horses worked. That didn't mean we shouldn't have built cars.
Now, to be completely impartial here, the skeptics have some incredibly valid counterarguments. Beyond the massive revenue LLMs generate, reasoning models layered on top of LLMs are rapidly improving at logic and math. Furthermore, researchers like Eric Zing point out a mathematical flaw in JEPA called representation collapse. If JEPA only predicts abstract embeddings without ever generating an observable output pixel to check against reality, it risks creating internal representations that are completely disconnected from the observable world, essentially hallucinating its own physics. Zing brilliantly calls this risk meditation in a closed room.
So the crucial point is this: generative AI and LLMs are incredibly useful, and they aren't going away for business tasks, coding, or content creation anytime soon. But if the ultimate goal is advanced machine intelligence, systems that can actually navigate the messy, unpredictable complexities of the physical world like humans and animals do without hallucinating, we might require a completely different cognitive core, a core built not on predicting the next word, but on observing the world, predicting abstract outcomes, and utilizing persistent memory.
As this billion-dollar divide shapes the next decade of technology and decides the future of AI architecture, it leaves us with one profound question to really chew on. Does true intelligence start in the mastery of language, or does it start in the physical world? Thank you so much for exploring this fascinating topic with me in today's Explainer, and keep questioning the future.